Okay, so hi everyone, welcome to my first virtual SI session. So just some reminders for virtual SI sessions, we don't want any students to turn on their cameras or mics since this video will be sent to the whole class. And then please communicate only through chat or with reaction buttons. And that's basically it for reminders about the virtual SI session. Just remember, just don't unmute or turn on your camera. But please do communicate through the chat so that you guys are still able to participate. So our agenda for today is we're going to start with a true or false activity to practice solubility rules. We're going to do a double replacement reaction practice problem. We're going to practice activity series and how to use it. And then we're going to do one molarity and one titration problem. And then we'll just have our closing activity. And if you guys have any questions, you guys can ask them. So this is our first activity. So here are 6 different true or false statements. So we'll just go down the list and you guys can just tell me through the chat whether it's true or false, and then we can go over any that people are confused about. Okay, so the first one is AgCl is soluble. Is this true or false? False, false. Yeah, I'm seeing people in the chat said false. Yeah, correct. AgCl is insoluble because it's a chloride, and Ag+1 makes chlorides insoluble. Okay, the next one is KNO3 is insoluble. Pratik says false, false, false. Yeah, you guys are all right. This one is, oh, sorry. This one is also false. All nitrates are soluble, so that's just something to remember. The next one is KCl is soluble. Is this true or false? True, true, true. Yeah, correct. True. KCl is soluble. The next one is a statement. So weak acids / bases completely ionize in water. True or false? I'm seeing people put true for this one. This one is actually, oh, okay. Now the falses are coming in. Yeah, this one's false. How would we correct this statement if we were to make this statement true? What kind? Strong acids. Yeah, correct. So strong acids are the ones that completely ionize and dissolve in water. Yeah, and those are on your solubility rules, like at the bottom. Yeah, good. Okay. The next one is PbI2 is insoluble. True or false? I'm seeing some people put true, true. This one is actually true, and that's because PbI2 is an iodide, and on our solubility rules, if iodide is next to Pb+2, it's going to be insoluble. It's one of the exceptions. So yeah, good job, everyone. And then number 6, BaOH2 is insoluble. Is that true or false? I see one true and one false. I'll wait for some more answers. False, 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 true. So this one is actually false because if you guys, I'll first write it in. On our solubility rules, if we go down to hydroxides, are usually insoluble, but if they're next to Ba+2, which this one is, it becomes soluble. So that's why BaOH2 would be soluble in water. Yeah. Yeah, we just need to remember to practice with the chart. Yeah, you guys will get better the more you guys do it. So good job on this activity. For the most part, you guys got almost all of them correct. So good job. Okay, we're gonna start my timer just finished, so we're going to start going over this problem. So we're doing barium chloride and magnesium sulfate. So you guys can just answer through the chat, but can someone tell me, I see 2 people already put the balanced net ionic reaction, but we're just going to go through it all together. So can someone tell me how we would write BaCl2's formula? Oh, I just said it. Oh my gosh. Okay, my bad. I was supposed to say barium chloride. BaCl2 plus, and then magnesium sulfate. How would we write that? MgSO4. Good, yeah. MgSO4. So those are our 2 species. And then what would be our 2 products that are made from this? I see BaSO4 plus MgCl2. Yeah, correct. And just for clarification, so we know that this has BA has a charge of +2 and SO4 has a charge of -2. So that's why there's no subscripts for this one. And Mg has a charge of +2 and Cl has a charge of -1. So that's why we put the 2 down here. But I see everyone already basically got that. So good job, everyone. So now we'll move on to the total ionic. So does BaCl2 break apart or stay together? Everyone is saying break? Yeah, correct. Ba plus 2 plus C. And then we always need to remember to include the coefficients. So would MgSO4 break up or stay together? Also breaks. Good job, everyone. So we have Mg. Okay, so now to the product side. So does BaSO4 break up or stay together? Stay together, stay together? Yeah, correct. This one is going to stay together, form a precipitate. So we always include the subscript S for solid. And then the last one is MgCl2, break up or stay together? Break, break, yeah, correct. This one is going to break apart. So Mg plus 2 plus Cl minus. Okay, oh, 2Cl minus. Let me add the subscript. I mean the coefficient. Okay, is there anything that we can cross off that we have doubles of on both sides to get to our net ionic? Cl and Mg, yes, correct. We'll just cross these off, and then our net ionic is just adding what we have left. So we have a subscript of a little s on this side for solid. So what subscript should we put for the Ba plus 2 and SO4 minus 2 to signify what state they're in? AQ, correct, yeah. So always remember to include the subscript. It just helps keep track of what state every element is in. Okay, so you're counting total number of ions. So on this side, it is the coefficients. You guys are right, and it would just be 1 plus 2 plus 1 plus 1. I was thinking of redox reactions. I'm so sorry, and then this one would just be 1 plus 2. So there's 3 on this side, and then there's more on this side. So the conductivity would decrease. Now we'll go to okay, so the first one, we'll start with activity series, PB. So in this one, we're deciding which of these 2 reactions would actually occur. So we'll use activity series for that. So we'll start with PB Al plus 3. So can someone tell me the charge of, of PB? 0, correct. And then Al plus 3. So Al plus 3 would just have a plus 3 charge. Yeah, correct. Okay, and then so since PB has a charge of 0, we know that it's getting oxidized. because in lecture, Dr. E explained that any metal with a charge of 0 wants to be oxidized. So I'll write that here. Metal with charge of 0 wants to be oxidized. And that's just a general rule for all activity series. If the metal has a charge of 0, it wants to be oxidized. So that's just one thing to remember when doing these kind of problems. So that would, by default, that would mean Y0. In lecture, it was explained that any metal element, when using activity series, has a charge of 0. It wants to increase its charge, so it wants to be oxidized. It's just a rule, kind of, just like a general guideline. And then by default, that would mean Al plus 3 is getting reduced. And then we'll do the next one, Pb plus 2. So this one's charge again 0 and plus 2. And in this scenario, Al is the metal with a charge of 0. So this would be getting oxidized. And by default, this is getting reduced. And we learned in lecture that whatever element is getting oxidized should be higher on the activity series. So if we were to find both of these elements on the activity series, Pb is right here and Al is right here. And the element that wants to be oxidized should be higher than the element that's getting reduced. So since Al is higher, that would mean that this scenario would actually have a reaction occur, and this one would not. Does that make sense? Or would anyone like me to explain it again? Or are we good with the first problem? Good? Okay. Yeah, so basically rule of thumb for activity series is whatever is being oxidized should be higher. Otherwise, the reaction can't occur. Okay, we'll go to the next one. Go down slightly. Okay, so the next one is similar to one of the practice problems that you guys have in the lab exam practice that Dr. E gave you guys. So it says, which of the 3 metal ions do react with, which metal ions do react with Fe? So for this one, we'll start with Fe. So, and we'll start with Pb plus 2, just since that's the first answer option. So Fe has a charge of what? You guys can just send in the chat. 0, correct. And Pb plus 2, just its charge. And so since Fe is a metal with a charge of 0, would it be getting oxidized, want to be oxidized, or want to be reduced? Oxidized, correct. And by default, that would just mean Pb plus 2 is getting reduced. So let's erase these. So let's find Fe on our activity series. And just as a reminder, activity series will always be provided to you, so it's not something that you need to like print out or remember or memorize or anything like that. And then let's find Pb plus 2. So we remember that whatever element is being oxidized, in order for the reaction to occur, the one that is being oxidized must be higher. So would Pb plus 2 occur or no? I see one yes. Anyone else? Yes, yes. Correct, yeah. So Pb plus 2, Fe plus Pb plus 2 is a reaction that would occur because Fe is higher on the on the activity series than Pb, and since it wants to be oxidized, this reaction would occur. Let's do one more in this way, and let's do the next one. Let's do Mg plus 2. So we have Fe plus Mg plus 2. So this has charge 0 plus 2. It's getting oxidized, getting reduced. So let's find Mg on our activity series, sorry. So we know that the element that wants to get oxidized should be higher. So would this second reaction occur or no? No, correct, everyone. So yeah, so this one would not occur. So now that we kind of get the idea that for this specific problem, Fe should be higher than the other elements, let's find all the other elements on this. So we have Al is right here, Ag is right here, Zn is right here, and then Cu plus 2 is right here. So based on where everything is, what would be, there's two more elements that would have a reaction occur, two more ions that would have a reaction occur. So can someone tell me the two other answer options that would have a reaction occur? DNF, Ag, and Cu? Exactly, yeah. It would be Ag and Cu, because we know that Fe is always getting oxidized in this problem. So Au, Fe must be higher, and the only ones it's higher for is Cu and Ag. Okay, good job everyone on this one. Does this one make sense? Or does anyone have any other questions about activity series or how to use them or anything like that? Or are we good? Good, okay, perfect. Okay, so it's been 2 minutes, so let's start going over this problem. So this problem says, how much NaOH in grams must be added to 200 milliliters of water to make a 1 molar NaOH solution? So this is just a molarity problem. So can someone tell me what the formula for molarity is? Moles over liter, yeah. So molarity is just molarity equals moles solute over liters of solution. So is there any of these variables so far that we can fill out based on what the problem gave us? So do we know the molarity? L and M, yeah, correct. So we know that the molarity is 1 molar NaOH equals moles. So we don't know the moles yet. And then liters of solution. So if we were to convert 200 ml to liters, what would our new value be in liters? .2? Yeah, correct. So just as a reminder, milliliters to liters, just divide by 1,000 and you'll get your liters. So now we'll just multiply by 0.2. So we got 0.2 moles NaOH. So the problem asked us in a certain unit. So what do we have to convert our moles to? Grams. So how would we set up this dimensional analysis? So we have, so what would we put on the bottom of this? 1 mole, everyone agree? Yeah. So we would put 1 mole of NaOH on the bottom, and then what would go on the top for this one? The molecular weight, which, thank you, is 40 grams NaOH. And in dimensional analysis, so we just canceled out the moles because now we're in grams. So let me scroll a little. So did anyone, was anyone able to get the final answer or calculate the final answer? 8. Correct, yeah. Our final answer is 8 grams NaOH. So good job, everyone. It's been 5 minutes, so we're gonna start going over this problem. Hopefully you guys were able to get through it, but if not, it's okay since we're gonna go through it together anyways. So with titration problems, I always like to start with first drawing a picture because it kind of helps keep everything organized. So that's our burette and our flask. So in the top, we have 17.9 ml. So we have 0.225 molar KOH, and we have 17.9 ml. And so we know we have 7.50 milliliters of an unknown acid, and we're trying to find the concentration of H3X. So we'll start with first getting the molarity formula. So we talked about it in the last problem, which is just moles solute over liters of solution. So what can we fill out from in this equation so far with the known numbers that were given so far? Molarities and liters. Yeah, correct. So we know that we have 0.225 molar KOH, unknown moles, so we'll just leave it as moles, and then liters of solution. So we have 17.9 milliliters. So what would that be converted into liters? 0.01979, yeah, 0.0179 liters. And just as a reminder for just general, but we just took 17.9 milliliters, divided it by 1,000, and that's how we got to 0.0179 liters. Okay, so then we'll just solve this just with algebra. Okay, so was anyone able to calculate the number of moles? So I'm seeing 0.0403 and then 0. Okay, so I'm gonna go with the answer that I got is also 0. Let me write it more on the side. Yeah, I also got 0.00403. This is the answer that I got as well. I think someone put the final answer for the problem, but we're still on moles of KOH right now. And then let me move it a little bit to the side so we can do dimensional analysis. So we have moles KOH, and we need to convert to moles of H3X. So again, oh no, you're totally fine. It's good. Okay, so we're in moles of KOH, which is our base, and we need to convert to our acid. So if this were just a regular problem with a monoprotic acid, it would just be 0.00403 moles. But since this acid is triprotic and has 3 hydrogens, how would we set up the dimensional analysis to find out how many moles of acid we actually have? So we'll just, what would go on the top and bottom essentially? So we'll start with the bottom. So what should go on the bottom? The KOH, yeah, definitely the KOH would go on the bottom. So I'm seeing 3 mole KOH. And then on the top, we would have, okay, so I'm seeing some people put 3 and some people put 1. So for this one, you would actually put 3 on the bottom, 3 moles on the bottom and 1 mole of H, because, so for this one, KOH, this itself only has 1 hydrogen, and H3X has 3 hydrogens. So to make 3 of the acids, to make 1 of the acids, you need 3 KOHs. Does that make sense for everyone? That's why we have 3 moles KOH and 1 mole of H3X. Yeah, good. Okay. Okay, perfect. So then did anyone get, and then that would just cancel out the moles of KOH and we're left with moles of H3X. So did anyone, yeah, someone asked, can you also write it like a molecular formula? Yeah, you can also do that, and that can help you figure out the mole ratio. But you can also just look at the number of hydrogens in the base and the acid and kind of find it from there too, whatever is easier for you. But yeah, you can definitely look at the molecular formula as well. Okay, did anyone calculate the moles of H3X? I'm seeing 0.00134 moles H3X. I'm going to scoot us down just a little bit. Okay. Okay, hopefully that's what everyone else got as well. So now we are in moles of H3X, but the question was specifically asking for concentration, and concentration always means molarity. So that means we have to find the molarity of H3X. So let's write out our formula. So moles, molarity. And so what would go on the bottom here? Liters, yeah. So we have 7.50 ml of our unknown acid. So what would that be in liters? I'm saying 0.0075. Okay, yeah, general consensus. Yeah, 0.0075 liters. So did anyone solve this on their calculator yet? $0.179. So our final answer would be 0.179 molar H3X. So make this smaller. Okay, so that's the completed problem. Does that make sense for everyone? Does anyone have any questions about molarity or titrations, mole ratio, how we set up the problem or anything like that? I'll wait like 30 seconds in case anyone has any questions, because titrations is usually one of the harder topics in Chem 1A. When would you use M1V1, M2V2? That's going to be in the kind of problem where it says, this is just like an example I'm thinking off the top of my head, but it would, or actually maybe I have one here somewhere. Not this one. This one. Maybe in here. Here. So this one is an example problem with that. So it asked how many milliliters of 5.5 molar NaOH solution must be used to prepare this. So usually it'll say used to prepare, and you'll have either 2 initials or 2 finals. And so usually they'll give you 3 numbers. And then you just fill out your initial M1V1 and your final M2V2. So something set up kind of like this is when you would use M1V1. Okay, I'm seeing some more questions. So let me go back in the chat. What are general steps for solving titration problems? So generally you start by, this is just like my way of solving them, but I start by drawing the picture first, just so you can visualize what you have. Then you do this first part with finding the moles of your base. And then your moles of your base is equal to your moles of acid. And if that's, that if you have a monoprotic acid, you would just leave it at that and find the molarity if it asks, otherwise you're done. Or if you have triproduct like this one, then you would do the mole ratios and then finish finding the concentration. But those are the general steps. Just start with the molarity problem and just do what you're given. Why we didn't use the M1V1 for this one? This one only has 2 numbers given to us, because this one is asking how much of one thing that we need. Are you talking about this problem or, oh, the titration? This one is because this explicitly tells you that this is a titration problem. And anytime, so anytime so some keywords for titration problems, they'll either use the word titration, either endpoint, equivalence point, things like that. When you read the problem, it gives you certain keywords that tell you that you're doing a titration. In M1V1 is not titration. M1V1 is used to prepare solutions. So like if I had like 3 molar HCl, but I need to make 1 molar HCl, that's just preparing a solution. That's when I would use M1V1, M2V2. Titration is the one that you guys actually did in lab, where you have the burette and you're titrating until the color changes. That's titration. And for that, you would do a process similar to how we did for this problem. What if we get grams in a molarity problem? So if you were to get grams in, oh my gosh. If you were to get grams in a molarity problem, you would just, where you have moles of solute, before you fill that out, you would just convert whatever you have from grams to moles. How did you get 3 moles of KOH? So the way that I got 3 moles of KOH is here. Let me change my highlighter color. So in KOH, you only have 1 hydrogen, but in the unknown acid, you have 3. So in order to make 1 acid, you need 3 KOHs. Does that make sense? It's based on the number of hydrogens. Does that answer your question, or do you want me to explain it a little bit more? Explain more? Okay, yeah. So basically so in a regular problem, like say you have oh my God, I'm writing in a highlighter. Give me a sec. Okay, so let's go down a little bit. So so say you have HCl and then you have KOH, right? So in HCl, you have 1 hydrogen, and then in KOH, you have 1 hydrogen. So the mole ratio is just 1 to 1, right? But say for our problem that we just had, we have H, 3X, and we have KOH. So in KOH, you have 1 hydrogen still, but you have now 3 hydrogens in your acid. So now the ratio is 3 to 1. So now in order to make 1 acid, you need 3 KOHs because there's only 1 hydrogen. So you would need 3 KOHs. I'll just erase this right here. And then, so now you have 1, 2, 3 hydrogens, and it makes up for the 3 that you have, the 3 that you have in the acid. Does that make sense? Does that clear it up a little bit? Yeah, it does. Okay, perfect. Yeah, and then you can also, yeah, someone suggested watching the lecture video. Yeah, Dr. E also explains this in some of her lecture videos. She does a problem like this in the titration lecture video, and in the lab, she uploaded a video of her doing lab problems for you guys. And she also does a problem with an unknown triprotic acid in that one as well. So if it's still confusing, you guys can check those out, and hopefully that will help. And then does anyone have any other questions about molarity, dilution, titration? I'll wait like 30 seconds. Titrations, I don't want to say 100% because I know more about lecture stuff, but I think your first lab exam is experiment 1 through 6, and 6 is titrations, I believe. So I think it will be on the exam, but correct me if I'm wrong because I don't know for sure. Like I just got your guys' lab schedule like last week for the first time. So I think it will be on the exam, but just make sure yourself just in case, because I don't want to give you misinformation. But yeah. Okay, so if no one has any other further questions about this, I'll share my presentation again really quick. So our closing activity for today is just, I'll open the chat again. Give me 1 second. Just discussing, anyone can just share in the chat key takeaways or favorite part of the session, or just questions, whether that's about content or SI sessions in general. Either way is fine. So, my gosh, and again, I'm so sorry about the double replacement reaction. I still feel so bad about that, so I'm sorry about that. But Yeah, so does anyone have any key takeaways or favorite part of the session or questions that they would like to share in the chat? Metals with charge of 0 want to be oxidized. Yeah, definitely important. Practicing concepts for molarity and titration. Nice, nice. Yeah. Okay. Activity series. Yeah, activity series is always one that is a little hard since you only use it really in lab. You don't get a lot of practice with it in lecture. So I'm glad we were able to go over that. Keywords, yeah. Okay, and then, oh, I closed the chat. Give me 1 second. Yeah, for the activity series, actually, Dr. E also posted, I think 2 videos, and she does like 4 or 5 practice problems with it. So definitely check those out because I think this will be on your lab exam. So it's good to practice with it a little bit prior. And good luck on your guys' practice exam. I hope you guys do well. Just some reminders, my next session is Tuesday, 12 to 1. And I think for my Tuesday session, I might do a little bit of titrations and then also start going over concepts from this week and a little bit of the earlier next week concepts. So I don't know for sure, I haven't planned it yet, but yeah, my next session is 12 to 1. And then this video, yeah, so this video is going to be sent out since you guys all attended the lecture, the session. This will be sent out to you guys as soon as it's done being edited. I just need to take out some of the times where we were just working quietly. So I'll take out those so it's like a concise video for you guys. And I'll send this out as soon as I'm done editing it. And then the recording will also be sent to the whole class 2 weeks prior to the midterm. But you guys will get it earlier than everyone else since you guys came to the session. But yeah, that's basically for the video. And yeah, I'll be sending the recording and then no problem. Thank you guys so much for attending and participating. I know it's a little harder since you guys weren't able to unmute or like talk in person. So thank you guys for participating. And that's all the content I have for you guys today. So unless anyone has any other questions, you guys are free to go. Will there be another session for next Saturday? My session, the Fridays, the Saturday sessions are bi-weekly. So not next week, but the week after. And you guys have a great day too. So thank you guys so much for coming. Have a nice weekend.